The objective of this lecture is to provide an introduction to Earth-centered, Earth-fixed coordinates and ground tracks. This lecture will be divided into the following parts. First, we will define Earth-centered, Earth-fixed coordinates. Next, expressions will be derived for inertial velocity and inertial acceleration in terms of Earth-centered, Earth-fixed coordinates. Third, definitions are provided of Earth relative longitude and geocentric latitude in terms of Earth-centered, Earth-fixed coordinates. And fourth, the differential equations of motion are derived for a spacecraft moving under the influence of central body gravitation in terms of Earth-centered, Earth-fixed coordinates. And finally, a MATLAB code is written to solve the differential equations and display ground tracks. And the ground tracks are going to be displayed on a Mercator projection. Of the Earth. So let's start with Earth-centered, Earth-fixed coordinates. So consider a spacecraft moving over the Earth. So let's start with this picture as follows. Now this picture looks as follows. So we have the Earth, And the center of the Earth is denoted as point O. The spacecraft in this particular case is going to be denoted by the symbol P. So P is the spacecraft. Now, attached to the Earth is a coordinate system which will be referred to as O together with the basis EX, EY, and EZ. Now, these directions, EX, EY, and EZ, are defined as follows. The top of the Earth, or the top of the sphere, is denoted, that point is denoted N, and N is the North Pole. Now, the circle that I've drawn in the middle, this is the equator of the Earth. If I take the great circle going from N and passing through the equator, that great circle then intersects at the bottom this point, which will be denoted S. S is the South Pole. Now, this line of longitude, as we call it, that actually goes from N through the equator to S, this is what's known as the prime meridian. And it actually passes through the Greenwich Observatory in Greenwich, England. Now, this basis, EX, EY, EZ, is fixed to the Earth. And the basis vectors themselves, EX, EY, EZ, are defined as follows. EX is along O to the intersection of the prime meridian with the equator. Then EZ is along ON, where N, as I defined, is the North Pole and O is the center of the Earth. And then EY is equal to EZ crossed with EX. Now, if we put the basis together with the origin O, then we have Earth-centered, Earth-fixed coordinates. So then, the point O, which is again the center of the Earth, together with the basis EX, EY, EZ is called an Earth-centered Earth-fixed coordinate system. Now we can revisit the diagram as follows. So we can add to this diagram three quantities that are of importance, which are the components of the position in Earth-centered, Earth-fixed coordinates. So what I'm going to do here is I'm going to draw these components. The components are, of course, as would be natural, denoted X, Y, and Z. So this component is X, this component is Y, and this component is Z. So it can be seen from this diagram that the position of P relative to O, which henceforth will just be denoted R, is equal to XEX plus YEY plus ZEZ. Now that's the position expressed in Earth-centered, Earth-fixed coordinates, or equivalently, the Earth-centered, Earth-fixed basis. And what we're also going to do, in order to make this a little bit easier for what's going to follow in this discussion, I'm going to say let E equal EX, EY, EZ. Now, using this information, we need one other piece of information, which is that's the rotation rate of the Earth. So I'm going to define the rotation rate of the Earth here. I'm going to call this omega EI, and I'll define it in just what's coming up here. I'm going to say let I be the inertial reference frame. Then the Earth rotates relative to I with an angular velocity omega EI. So in other words, omega EI is the angular velocity of the Earth as viewed by an observer in the inertial reference frame I. And you can see that the angular velocity is about the axis EZ. So omega EI lies along EZ, which is equivalent to saying it lies along ON. Now, given that, we're going to actually define the rate. We're going to say let omega be the rotation rate of the Earth. And again, it's relative to the inertial reference frame. So then, omega EI is equal to omega times EZ. Now, it's important to understand that to any reasonable approximation, the rotation rate of the Earth is essentially constant. What that means is that we can approximate it as a constant. So that's equivalent to saying that we can take omega to be a constant. Now, this constant is approximately as follows, which is that we know that the Earth rotates once on its axis of rotation in approximately 24 hours. So that implies that omega is equal to 2 pi, because it goes 2 pi radians in 24 hours. So that's radians per hour. But we don't want this in radians per hour. We normally work in MKS or SI units. So that's equivalent to saying that omega is equal to 2 pi over 24 radians per hour times 1 hour in 60 minutes times 1 minute in 60 seconds, which gives that omega is equal to 2 pi divided by 24 times 60 times 60 radians per second. So that's the rotation rate of the Earth. And that's the rotation rate that's typically taken if you're just approximating things to be a 24-hour period. So now we have everything that we need in order to be able to work forward with the derivation of inertial velocity and inertial acceleration in terms of Earth-centered, Earth-fixed coordinates. Now, in order to make it easier to be able to write the term Earth-centered, Earth-fixed over and over again, we're going to make the following abbreviation, because we're going to be using this quite often. We're going to say ECEF is the abbreviation for Earth-centered, Earth-fixed. And we'll use that abbreviation in the remainder of this lecture. So now we are going to derive expressions for inertial velocity and inertial acceleration in ECEF coordinates. So we're going to start as follows. So we have the position is equal to XEX plus YEY plus ZEZ. So then the inertial velocity is equal to the rate of change of the position in the inertial frame. But the position is expressed in coordinates fixed in the Earth. So this is equal to the rate of change of the position as viewed by an observer fixed to the Earth plus the angular velocity of the Earth in the inertial frame crossed with the position. But dr, dt, and E is the velocity as viewed by an observer fixed to the Earth. So that implies that VI is equal to VE plus omega EI crossed with R. Now, what we can do at this point is we can substitute in the expressions, which is we know that VE is equal to dr dt in E, which is equal to x dot EX plus y dot EY plus z dot EZ. And also, we know that omega EI crossed with R is equal to, well, we have the expression for omega EI. It's omega EZ crossed with XEX plus YEY plus ZEZ. So that's equal to, well, EZ crossed with EX is EY, and EZ crossed with EY is minus EX. So we get minus omega Y EX plus omega X EY, and then EZ crossed with EZ is 0. So that implies that the inertial velocity is equal to, well, let's add these terms together. We've got x dot minus omega y times EX plus y dot plus omega x EY plus z dot EZ. So then the inertial acceleration is equal to the rate of change in the inertial frame of the inertial velocity. But again, the inertial velocity is now expressed in Earth-centered, Earth-fixed coordinates. So this is equal to the rate of change as viewed by an observer fixed to the Earth of the inertial velocity, and then plus omega EI crossed with VI. Now let's take each of these terms in succession. d dt and E of VI is equal to, well, if I do the derivative out, because the angular velocity of the Earth, that rotation rate is constant, so we wind up with x double dot minus omega y dot EX plus y double dot plus omega x dot EY plus z double dot EZ. The next term is omega EI crossed with VI, which is equal to omega EZ crossed with x dot minus omega y EX plus y dot plus omega x EY plus z dot EZ. And that's equal to, well, again, EZ crossed with EX is EY, and EZ crossed with EY is minus EX. So we get minus omega times y dot plus omega x EX and plus omega times x dot minus omega y EY. And then the third term is 0 because EZ crossed with EZ is 0. So therefore, the inertial acceleration is equal to, well, if we add up all these terms, we've got x double dot minus omega y dot, and then I have another minus omega y dot, and then I have minus omega squared x times EX. And then the next term is plus y double dot plus omega x dot, and there's another omega x dot minus omega squared y. And then the third term is just z double dot. So this implies that the inertial acceleration is equal to x double dot minus 2 omega y dot minus omega squared x EX plus y double dot plus 2 omega x dot minus omega squared y times EY plus z double dot EZ. So before we move on to the derivation of the differential equations of motion, we want to discuss one more topic with regard to Earth-centered, Earth-fixed quantities, and those are ground tracks. And really what we're going to be discussing here are longitude and latitude. And specifically, we're actually going to be discussing Earth relative longitude and geocentric latitude. So recall that the triplet XYZ provides the information about the ECEF position. And what we actually had in the diagram previously, which I'll draw again here, is that we have the spacecraft at point P and we have the center of the Earth at point O. Now there are 3 coordinates. They are X, Y, and Z. And so if we look at these quantities, X, Y, and Z, we can project a point P into the XY plane. The point P into the XY plane, we can call that point Q. Now, the angle theta, because this direction that I've labeled here is EX, this direction is EY, and this direction is EZ. So the angle between EX and this direction OQ, I'm going to call it theta. That's what's called the Earth relative longitude. The angle between OQ and OP is phi. That's what's called the geocentric latitude. And the way you compute these two, so theta is the Earth relative longitude, and it's actually equal to the 4-quadrant inverse tangent of y and x. Phi is what's called the geocentric latitude, and it's actually equal to the inverse tangent of z and the square root of x squared plus y squared. Now, you can actually visualize these two quantities on what's called a Mercator. So a Mercator is a two-dimensional plot of phi versus theta. And although I don't have a lot of room on this slide, you don't really need a lot of room for it. It's basically a plot that looks like a world map. And on it, if you actually plot the longitude versus the latitude, so theta would go on this axis and phi would go on this axis. You can plot phi versus theta, and this curve that you get when you do that, which is on the Earth, this is the ground track. And this will come in handy when we actually want to visualize things later on a Mercator projection. This is basically a Mercator projection. And it provides a lot of useful information because it tells you the point over the Earth that you actually are. And it's given in terms of these two quantities, which are the Earth relative longitude and the geocentric latitude. So we're gonna use this later on. Now we're going to go back to actually developing the differential equations of motion, but now we have really all the quantities that we need with regard to Earth-centered, Earth-fixed analysis, so we can use it as we actually move through the remainder of this lecture. So next, we're going to derive the differential equations of motion. So, in order to start this derivation, the first thing we note is that the only force acting on the spacecraft is that of gravitational attraction by the Earth. So what that implies is that the force is equal to the force of gravitation, which is the force of big M on little m, which is equal to minus g times little m over big M times r cubed times r, where little m is the mass of the spacecraft and big M is the mass of the Earth. And this notation F, M, little m in that order is the force exerted by M on little m. So now that we know that, so we know from Newton's second law that the force is equal to the mass times the inertial acceleration. So that implies that minus g times little m big M all divided by r cubed times r is equal to the mass times the inertial acceleration. So we can drop the little m out of this equation, and we can also make the substitution. We can say let mu equal g times m, which will be defined as the gravitational parameter. And in terms of the gravitational parameter, we wind up with minus mu over r cubed times r is equal to the mass times the inertial acceleration of the spacecraft. So that's what we're going to work with for the rest of the derivation. So first, we have that r, which is equal to the magnitude of the position, is equal to the square root of x squared plus y squared plus z squared. So then we can actually write the force out a little more compactly, although we're not going to use the square root. We're just going to keep it that way. We get minus mu over r cubed times xex plus yey plus ez. And that has to equal the acceleration in I, which is equal to x double dot minus 2 omega y dot minus omega squared x ex, and then plus y double dot plus 2 omega x dot minus omega squared y ey plus z double dot ez. So if we equate components, then we wind up with the following three differential equations. And these differential equations are minus mu over r cubed times x is equal to x double dot minus 2 omega y dot minus omega squared x. The second differential equation is minus mu over r cubed times y is equal to y double dot plus 2 omega x dot minus omega squared y. And the third differential equation is minus mu over r cubed times z equals z double dot. Now define the following relationship. So suppose that B is a vector. Then B expressed in the basis E1, E2, E3, which can be defined as by little e, is given as B is equal to B1, E1 plus B2, E2 plus B3, E3. So then B expressed in E is equal to the column matrix B1, B2, B3. Now, what we can do with this is we can actually define what's called a skew symmetric matrix. So given the vector B, the skew symmetric matrix associated with B, in this case E, is given as, or is defined as, B, and what we're going to call this is BE skew. And it's equal to the following. It's got zeros on the diagonal, and it has minus B3, B2, minus B1 in the upper diagonal, and then it has B3 minus B2 and then B1 in the lower diagonal. And this is the skew symmetric matrix. Associated with B expressed in E. And now we can use this result to be able to simplify the equations that we just derived. So now let omega EI skew in E equal the skew symmetric matrix associated with omega EI expressed in E. Well, we can recall that omega EI is equal to omega EZ, which implies that omega EI expressed in E is equal to 0, 0 omega. So from that, we actually get that omega EI skew expressed in E is equal to, well, if we follow the rule that I just described, we get minus omega, omega, and then we get zeros everywhere else. So now we can use omega EI skew in E to rewrite the differential equations in a more compact form. So in particular, in order to do that, we're going to use the following substitutions. We're going to say let RE equal X, Y, and Z, and we're going to let VE expressed in E equal X dot, Y dot, Z dot, which is going to be defined to be Vx, Vy, Vz. So recalling the differential equations, we have the following. We have x double dot minus 2 omega y dot minus omega squared x is equal to minus mu over r cubed times x. The next differential equation is we have y double dot plus 2 omega x dot minus omega squared y is equal to minus mu over r cubed times y. And then the third differential equation is z double dot is equal to minus mu over r cubed times z. So these last equations can be rewritten as follows. So rewriting, we have, I can write this as a column matrix, x double dot, y double dot, z double dot, and then the next term is plus 2 times, well, this matrix that I just defined, which is 0, 0, 0, minus omega, 0, 0, omega, 0, 0, times x dot, y dot, and z dot. And then the last one, which I'll show in just a minute, is equal to plus 0 minus omega 0, omega 0, 0, 0, 0, 0, the whole thing squared, times x, y, and z is equal to minus mu over r cubed times x, y, and z. Now, the first two terms are probably fairly clear, but the last term may be a bit of an issue, so I'll explain the last term as we go through right now. So now we have the following, that this matrix 0 minus omega 0, omega 0, 0, 0, 0, 0, when I square it, it's equal to itself times itself. And so when I do this product between this matrix and itself, I get the following result. So if we just multiply it out, row by column, first row times the first column gives me minus omega squared. The second row times the first column gives me 0, and the third row times the first column gives me 0. Now let's do it again. The first row times the second column gives me 0. The second row times the second column gives me minus omega squared. And then I get 0. And then the last column is all zeros because nothing appears. So this winds up giving me minus omega squared times the matrix 1, 0, 0, 0, 1, 0, 0, 0, 0. And now that, because z doesn't have any omega terms, that's equivalent to just multiplying by minus omega squared, which is what I had originally. So now what I can do is that I can use all of this information together with the differential equations that I just rewrote in the previous form to be able to write this in an even more compact form. So now recall that omega EI skew expressed in E is equal to this matrix that I have defined, 0 minus omega 0, omega 0, 0, 0, 0, 0. And also recall the previous expressions that I had for R expressed in E and VE expressed in E, and we wind up with the following result. And this result is as follows. So we have that R expressed in E is equal to X, Y, and Z. And then VE expressed in E is equal to Vx, Vy, Vz. And that implies that the acceleration expressed in E, that's the Earth relative acceleration expressed in E, is equal to Vx dot, Vy dot, and Vz dot. So in terms of the above notation, we have that the acceleration is viewed by an observer fixed to the Earth in ECEF coordinates plus 2 times the skew symmetric matrix omega EI skew in E times the Earth relative velocity expressed in Earth-centered, Earth-fixed coordinates plus omega EI skew in E times omega EI skew in E times R expressed in E is equal to minus mu over R cubed times the position expressed in E. So then, solving the last equation, for AE expressed in E, we have that AE, which is the Earth relative acceleration, expressed in Earth-centered, Earth-fixed coordinates, is equal to minus mu over r cubed times r expressed in E. That's the first term. And we have minus 2 times omega EI skew expressed in E times VE expressed in E minus omega EI skew expressed in E times omega EI skew expressed in E times R expressed in E. So now we note that the rate of change of the position expressed in Earth-centered, Earth-fixed coordinates is equal to the Earth relative velocity expressed in Earth-centered, Earth-fixed coordinates. Now that's the same thing as just saying that x dot, y dot, and z dot is equal to vx, vy, and vz. The next equation is that the rate of change of the Earth relative velocity expressed in Earth-centered, Earth-fixed coordinates is equal to the Earth relative acceleration expressed in Earth-centered, Earth-fixed coordinates. Now that's equivalent to saying that Vx dot, Vy dot, Vz dot is just equal to Axe, Aye, and Aze. Now, given the last set of equations that we just derived, we can then write that d dt of the position expressed in Earth-centered, Earth-fixed coordinates is equal to VE expressed in E. That equation stays the same. So it's the next equation that reads different, and it reads different in the following way. Is we have d dt of VE expressed in E is equal to minus mu over r cubed times r expressed in E, and then minus 2 omega EI skew expressed in E times VE expressed in E, and then minus omega EI skew expressed in E, the whole thing squared, times R expressed in E. Now, this last set of equations is a system of 6 first-order differential equations. And these differential equations are in the variables x, y, z, vx, vy, and vz. And these equations are actually not hard to implement in MATLAB, and we could actually implement them quite straightforward if we just actually go through and we do exactly what the equations tell us to do. So we're going to go ahead and we're going to perform an implementation in MATLAB to see how this actually plays out when we actually solve these equations numerically. So in this part of the lecture, we are going to develop a MATLAB code that solves the two-body differential equations that we developed earlier in the lecture. Now recall that those two-body differential equations were for a spacecraft under the influence of gravitation, and everything is expressed in Earth-centered, Earth-fixed coordinates. So this development of MATLAB code is going to consist of writing three functions, and these three functions are given as follows. They are SkewSymmetric.m. That's the first function I'm going to write. The second one is going to be two-body ODE Ecef, and the third one is going to be two-body main. Now, the first function, which I'll open up now, which is empty right now, and I'm going to create it. This is a utility function. This function is basically the function that I had derived in the lecture, which takes a vector and produces a skew symmetric matrix from that vector. So I'm going to call the vector, which is the input, A, and the skew symmetric matrix, I'm going to call it A skew, which is consistent with what I had done when we actually wrote the math out. So now A skew is equal to the following. It's 0 minus A of 3, A of 2. That's the first row. The second row is A of 3, 0, and minus A of 1. And then the third row is minus A of 2, A of 1, and 0. Now this matrix is going to be used in the remainder of the code. So first thing we're going to do is we're going to go over to our MATLAB command window, and we are going to make sure that we can actually run this function successfully. So I'm going to create a fictitious vector. I'm going to call it A, and I'm going to say A skew is equal to skew symmetric of A, just to make sure this runs. Now you can see that it does produce a 3 by 3 matrix, and that 3 by 3 matrix is in fact skew symmetric, because if I take A skew and I take its transpose and I take negative that, I get back the same matrix. So that's my indication that it is a skew symmetric matrix, because the definition of a skew symmetric matrix is one that is equal to the negative of its transpose. So now we have done that function. So that one is finished, and we can move on to the next function, which is I'm going to call this two-body ODE Cef. Now this function is the one that is used by the ODE solver to solve the differential equations. Now this one's a little bit more complicated, so I have to be a little bit careful, but it has to be in the format that ODE 113 enables one to use when calling the ODE solver. So it's got to take in T, it's got to take in PV, and I'll explain what these are in just a minute. And it's got two parameters, mu and omega e. Now this is because in this particular case I have the gravitational parameter, but I also have the rotation rate of the Earth. So the two parameters are, like I said, the gravitational parameter. So mu is the gravitational parameter, and omega e is the Earth rotation rate. Now the other inputs, which are important, of course, time is the first input, but PV is my state. It's actually my position and velocity, which is why I called it that. So PV is the state, which is equal to position and velocity. Now these of course are in Earth-centered, Earth-fixed coordinates. So what I'm going to do now is I'm going to pull off the relevant parts of this vector PV. So PV of 1 colon 3, well, that's my position. So this is my position. And then VV is PV of 4 colon 6, and this is my velocity, and it's actually my Earth relative velocity. Now remember, everything here is expressed in Earth-centered, Earth-fixed coordinates. And it's also important to understand that I use these symbols V because it gives me an indication that this is a vector, right? Because in these equations that I'm about to develop, I also need the radius. So the radius I'm going to call R, and it's going to be the norm of the position. And notice I don't have a V on this thing because it's not a vector. So now what I can do is I can set up the differential equations. And the differential equations themselves can be written in a nice compact way now that I've done this. So RV dot is equal to VV. That's the first equation. And the second equation is all of that stuff that we had developed when we wrote down the system of differential equations when we had derived it. So it's equal to minus mu over r cubed times rv, and then minus 2 times omega skew, and I'm going to get to omega skew in just a minute, times vv, and then minus omega skew squared times RV. Now, what is omega skew? Well, omega skew is equal to skew symmetric of omega EI, where omega EI is the angular velocity of the Earth relative to the inertial frame. And it's equal to 0, 0 omega E. Because remember that the angular velocity of the Earth relative to the inertial frame is about the axis that is in the northern direction. So it's about the North Pole, right? So now what we can do is we can take this information and we can put it all together into these equations. We're actually done with most of it. We have one more step that needs to be dealt with, which is we need PV dot, which is the output, and that's equal to RV dot VV dot. So now we should have everything that we need. But before we actually move on to the rest of the code, we should test this code and make sure that it actually works. And this is an important part of actually coding anything, is that we know that a function works. So what I'm going to do is I'm going to go back to my MATLAB command window, and I'm going to create some fictitious values. I'm going to say t is equal to 0. I'm going to say PV is equal to 1, 2, 3, 4, 5, and 6. And this is just done, it's just random. I'm just trying to make sure the function works. And then I'm going to say mu is equal to 1, and I'm going to say omega E is also equal to 1. Now these are not the correct values, but they will give me the possibility of being able to evaluate this function and make sure that it actually works. So the inputs are t, PV, mu, and omega E. So let's see if this function actually produces a value. Well, it does. And you'll notice that it produces 6 values, and there doesn't seem to be anything fundamentally wrong with any of these. It seems to work perfectly fine. So now we actually have that function coded. So now the next thing we're going to do is we're going to code this main function. Now this main function is the one that requires a little bit more work. So we're going to open up two-body main. And two-body main is going to need some information in order to proceed. The first one is we need the gravitational parameter. Now for the Earth, the gravitational parameter is 398600, and that's in units of kilometers cubed per second squared. That's the first one. Omega E, as an approximation, is equal to 2 pi divided by 24 times 60 times 60. Now that number comes from the fact that the Earth rotates 2 pi radians in 24 hours, and 24 hours is equivalent to 24 times 60 times 60 seconds. So this is in units of radians per second. Now, in addition to that, we need the following information. We need initial conditions. So in the initial conditions that we're going to be given here are going to be RV0, and that's going to be some value, and VV0, and that's some other value. So we are going to retrieve these values from another file that I created just because we're trying to demonstrate how this process works. I'm not going to explain where these numbers came from, but we're just going to use the values that I give you, and then we'll work from there. So now we're going to actually put these numbers in. and these numbers are going to be the following. So we're going to use these two values. Now these values, like I said, are not values that I'm going to explain where they came from, but we're going to use them in the simulation because they produce good results, and it's an orbit that actually makes physical sense. So we are going to use these values together with the setup for ODE 113. And just to be, make things easier with ODE 113, we're going to go 10 hours on the orbit. So we'll propagate for 10 hours. So that means my t-span is going to equal, and again, I'm just pulling these numbers out just for demonstration purposes, lin space t0 tf, and I'll use 500 points. Now what I'm going to do is I'm going to set the options equal to, using the ODE set command, to rel tall and 10 to the negative 8th. And then what I'm going to do is I'm going to set the ODE solver up. So this gives me T out, P out is equal to ODE 113 at two-body ODE ECEF, and then T span, and then PV0, which I have yet to define, which I will in just a minute, and then my options, and then mu and omega E, which are my parameters. So PV0 is equal to RV0, VV0. So now once I have that, I should be able to run this function two-body main. So let's go back over to the MATLAB command window and let's see what happens. Two-body main. So there's an unrecognized function here. So of course I didn't name these correctly, so I've got to go back and fix them. So let's run it again. And now there's still an unknown name in here because I didn't save the file. So let's clear the screen again and run it. Now it runs. Now you see that we get T out and we get P out. And now what we're going to do is we're going to compute the ground track for this trajectory. So the ground track is done as follows: is that theta is the Earth relative longitude, and it's equal to the 4-quadrant inverse tangent of y and x, and then phi, which is the geocentric latitude, is equal to the 4-quadrant inverse tangent of z with the square root of x squared plus y squared. Now I need to pull off x, y, and z. So x is equal to p out colon comma 1, y is equal to p out colon comma 2, and z is equal to p out colon comma 3. So now I can compute these quantities and I can plot the ground track. And I have actually, this is Earth relative longitude and geocentric latitude, and then down here is plot the ground track. And the ground track is going to be plotted with a function that I have created earlier called Mercator Display, and it takes the Earth relative longitude and the latitude and it computes the ground track. So now let's do this again and see if we can get this to work. Two-body main. This is an invalid expression, and of course I forgot a parentheses, so we have to close those parentheses. And now let's try it again, and we can see that it runs and it produces a ground track. And you can see that this ground track that it produces is a plot of latitude on the y-axis and longitude on the x-axis, and this is actually the track over the Earth that the spacecraft makes as it moves. Now I have done 10 hours, and so my initial condition is set in such a way that I'm propagating for 10 hours, and this is what the spacecraft looks like as it actually moves over the Earth. These ground tracks are actually used in analysis because you need to know when you're dealing with Earth orbiting spacecraft where the spacecraft is over the planet at any given point in time, because that's where you can actually observe and you can do whatever operations you're trying to do with the spacecraft itself. So the ground track is really, really important. And you can actually see that this ground track follows a very well-behaved shape, which makes sense because that's what you would expect for a trajectory that's continuous as a function of time. And so this is a nice looking plot, and it gives us a way of being able to visualize what's going on. If we actually go back now to the code, we actually see that the code now consists of 3 parts. One is this main file, which allows me to set up all of the quantities that I need for my problem and call the differential equation solver. And in addition to that, it allows me to be able to output the information that I'm interested in. In this case, that information includes computing the ground track. So that's the last part of this file. And then this main file, which calls ODE113. ODE113 in turn calls this function 2-body ODE-Ecef, and then that function calls this function Skew Symmetric, which I needed in order to be able to compute the differential equations of motion as part of my numerical computations in this problem. So that basically gets me to the end of this particular part of the lecture, where we actually have done the numerical demonstration, and we can finish this demonstration now. And just realize that ground tracks are really important in orbital analysis, and this simple tutorial gives you a way of being able to figure out how to compute ground tracks if you're given the ECEF position and velocity. And so that's the end of this numerical demonstration. So that takes us to the end of this lecture, and we can summarize this lecture as follows. So the first thing was we defined Earth-centered, Earth-fixed coordinates. And then we developed expressions for the inertial velocity and the inertial acceleration. Expressed in Earth-centered, Earth-fixed coordinates. And then what we did was we took a little brief excursion to discuss ground tracks. And in particular, they were discussed in terms of Earth relative longitude and geocentric latitude. And then finally, the differential equations were derived for a spacecraft in motion over the Earth, and then after deriving those differential equations, a MATLAB simulation was developed. And now, this approach for being able to implement things in MATLAB once you're done actually deriving equations is pretty useful, and we're gonna see more of it. As you actually study more orbital mechanics, you'll have to implement things in MATLAB. So this gives you a basis for being able to do that. So we'll we'll stop this lecture here and we'll pick it up next time.